I'm Anna Middleton. Anna is an expert on compact binaries and rotational wave observations with more than one instrument, both with LIGO and with pulsar timing array. And more recently, also she's getting into the domain of LISA. She works on all the frequencies that we have currently available and will soon be available with LISA. From the very low frequency of PTAs to LIGO with LISA in between. And she started out as a PhD student at the University of Birmingham, working with Alberto Vecchio at the time already on PTAs and LIGO sources. And then she moved on as a postdoc to the University of Melbourne in Australia. She was also affiliated with Swinburne, I believe, at the time. And then she came back to the UK, was a fellow at the University of Birmingham. And today she's going to talk about distinguishing black hole and neutron star binaries from double white dwarf systems in this.
Thank you. Yeah, thank you very much for the introduction, and thank you also for the opportunity to come visit and speak to your group. It's been really nice to chat to you all so far, and I look forward to this afternoon as well. Yeah, so this is about whether we can distinguish black hole and neutron star binaries from double white dwarf systems in LISA. So as UZH said, I'm relatively new to LISA. I'm sure a lot of people in the room know a lot more about it than me, but we'll do an overview of gravitational wave observations so far. I'll talk about the current mission status for LISA, the gravitational wave sources we can expect, and then we'll have a look at the project that we've been working on in Birmingham about distinguishing the black holes and neutron star binaries from the double white dwarf systems. Okay, so far, this is an overview of the gravitational wave observational windows. So at the top, you see the different types of facilities for gravitational wave observation. So ground-based, space-based like LISA, pulsar timing array, and the cosmic microwave background polarization experiments. I won't say anything about those because I don't know anything about that. Very, very low frequency. But as these, you're also seeing the scale of the frequencies of the sources that these facilities are interested in. And underneath, so from high frequency to lower frequency. And then underneath here, you can see the different types of sources. So ground-based observatories like Virgo Cagra are interested in, of course, emerging black holes and neutron stars, supernova, spinning pulsars. So this is continuous gravitational waves from a rotating neutron star. And as we move down in frequency, you have different types of sources that you can access with different types of facilities, and then moving all the way down to supermassive black hole binaries with pulsar timing arrays. So to go, just to have a short recap of what has been seen up till now. So if we go back to the Hulse-Taylor binary, this was the first observational evidence of gravitational waves. So the binary was discovered in 1974. It's a neutron star and a pulsar. And by long-term observations of radio signals from the pulsar, you can monitor the orbital decay. And so you can see at the bottom here, these observations lasted many, many years. So 1975 to 2005 at this stage. And the orbital decay precisely matches the prediction from general relativity for gravitational wave radiation being emitted from this system. So this is the cumulative shift of the periastron, so the sort of orbital decay movement, and the prediction from general relativity, and then the data points are overlaid on top of it. So this was the first observational evidence for gravitational waves, and then moving into it. So I've got this diagram at the top here so we can keep track. So we're in ground-based observations for this slide. So it's now 10 years of ground-based discoveries with gravitational wave astronomy, really. So in 2015, the first detection of a binary black hole merger, GW150914. So this is the data that was seen at LIGO Hanford and LIGO Livingston of a binary black hole merger, and each of the black holes had about 30 times the mass of the sun. And then in 2017, there was the first detection of a binary neutron star, 17817. 2021, the collaboration shifted into catalogue production. Well, this happened earlier actually, but this is the third gravitational wave transient catalogue, which contained 90 events from observing runs 1 to 3. And the ongoing observing run 4 announced the 200th candidate just last month. So at the moment, right now, there's a commissioning break at the sites, and then they'll pick up observations. I don't remember the exact date, but it's probably about a month off. And then switching down to low frequency pulsar timing arrays in 2000. So this is a decade-long effort to monitor an array of pulsars all over the sky. So using radio observations of the timing of the pulse. So to rewind a little bit, you have a pulsar, which is like a very stable clock, and you can predict when you expect the pulse to arrive. And by monitoring a set of pulsars, you can search for low frequency gravitational waves by looking for changes in the arrival time from the different pulsars. And in 2003, there was evidence announced for the presence of a gravitational wave signal in the pulsar timing array data. And the current and ongoing work is to strengthen this evidence by using the full international pulsar timing array data sets. So individual groups release their data and their searches, and now the challenge is to try and bring all these data sets together. Okay, so now we'll get to LISA. So LISA is the Laser Interferometer Space Antenna. It's 3 spacecraft. It will be 3 spacecraft separated by 2.5 million kilometers, and it will be in an Earth-like heliocentric orbit. It's a large-scale mission led by the European Space Agency with NASA as well. And the observation window will be, as you see here, between what you can do with LIGO, Virgo, Cagra and pulsar timing arrays. So this is showing the predicted strain amplitude spectral density, so the sensitivity of the instrument and the different types of sources that you might see with LISA. So I'll say a bit more about these later in the talk, but things like galactic binaries, stellar mass black hole binaries, and massive black hole binaries, and extreme mass inspirals. So in the run up to now, it's been quite a long journey for LISA, and I've only been involved in the last couple of years. So in 1993, there was the LISA proposal. In 2015, the LISA Pathfinder mission launch, and this demonstrated the technology that was needed for LISA. Just last year, ESA formally adopted the LISA mission, and this marks the transition from a study to a mission, and it's the sort of beginning of production of the actual of the instrument to build it. Later this year, the LISA prime contractor will be announced, and then in 2035 is the current scheduled launch date. So I'm part of the LISA ground segment team, so I won't say too much about this, but just to overview it, this is how the organisation is structured. So you have the spacecraft, the Mission Operations Centre, the Science Operations Centre, and then various ground segment teams. So I work in DDPC, the Distributed Data Processing Centre, which is the team comprised of ESA member states and also non-ESA member states that have committed to contribute to the mission. And there's an equivalent ground segment team with NASA. So we sit down here, and then this is performance and operations, where you model the instrument, and there's a lot of interfaces, as you can see, between all of these systems. But not to say too much about that. Let's go on to gravitational wave sources. So LISA will see many different types of sources, from massive black hole binaries, stellar origin black hole binaries. So these are the kinds of systems that you might expect to see in LISA that sweep through the frequency band of the LISA sensitivity bucket, and then a few years later could arrive in the LIGO, Virgo, Cagra sensitivity band and merge. So LISA could be in a situation where you see a system like this, and you can say to the ground-based facilities, make sure you're observing during this week, because there's going to be something very nice to see. And then extreme mass ratio in spirals, where you have a large supermassive black hole with a small, much smaller thing orbiting around it. And then what we're interested in for the purpose of this talk is the double compact objects. So these are galactic and local group double compact object systems, the majority of what LISA will see will be double white dwarf binaries. So there's a large population expected within the galaxy. And so this is from the LISA Red Book. You can see I guess the galactic population of these systems, but there'll also be black hole and neutron star binaries within this population. And this is what we're interested to see, whether or not we could distinguish them from the white dwarf binaries. So what we expect is well, a combination of individually resolvable white dwarf binaries. So these are what's called the verification binaries, systems where you have already observed them electromagnetically and you expect to see them in the LISA data. And there will also be a background of a confused population, so where you can't distinguish between the individual sources. So, and then, as I say, what we're interested in is seeing if we can find the black holes and neutron star binaries amongst these systems. And just to note that these are near monochromatic signals, so we're much earlier in their evolution than things that you would see with LIGO, Virgo, and Cagra. So we're not observing the merger, we're just observing the early in spiral. So they're almost monochromatic in the data. Okay, so the question we're asking is, can we tell them apart from the others? Okay, so this project, we're looking, so as I say, we want to be able to test this and see if we can identify them. And the challenge is to pull them apart from the white dwarf systems. So here we'll go through the various steps of the method that we've done, and along the way we'll show results and describe what we might expect in the end from the LISA mission. So I guess step one will be to select the binary systems that we want to simulate. Then we'll generate the LISA data using those systems. We do parameter estimation for each of the systems to see how well we were able to measure the key parameters that we need. And then we can ask ourselves, were we able to tell whether or not they were white dwarf binaries? Okay. So step one, we select the systems. So we're using a galactic catalogue from WAG et al. 2022. And in that paper, they simulate a galactic population of double compact objects. And then they take a look at what they get in terms of black hole binaries, black hole neutron stars, and then neutron star binaries as well. So this is showing the amplitude spectral density that they get from their population, the LISA sensitivities underneath. So when I was saying earlier about the confused white dwarf binary population, that's what makes this bump in the sensitivity of LISA. And then above that, we expect to be able to resolve individual louder systems. Okay, so this is the full population that they simulate. And then down here, you can see the three different source types that we're interested in. So for our purposes, we take their population, their catalogue, which they've fully released with the paper, and we draw a set of 100 of each type of system for our study. So yeah, 100 of each. And then here we're showing the draw that we've made. So this is the component masses, so primary mass, secondary mass. We always assume that M1 is bigger than M2. And then the binary black holes in purple, black hole neutron stars in green, and then the binary neutron stars in orange. So you can see they fall into different areas. And I think the way that the catalogue distinguish between them is purely based on the masses. Okay, and then as a spoiler, later on, so what you see here is the frequencies. So you see you get a range of frequencies of the systems, which is what's indicated by the color bar. And then as a slight spoiler, the circled ones are the ones that we can measure the parameters that we're interested in, but we'll get to that later. Okay. So we've selected the systems to simulate. The next step is to generate the data. So to to model a gravitational wave signal in LISA that we expect from these systems, we need 11 parameters. And several of these parameters can be directly taken from the catalogue, but the ones that cannot, we draw randomly. So here we've got the amplitude of the gravitational wave signal. So this comes from the catalogue. The inclination angle of the binary system. This is drawn. The polarization angle of the gravitational wave. So this is also drawn. The sky position, ecliptic longitude and latitude we take from the catalogue. The phase we draw. The orbital eccentricity we take from the catalogue. The initial periastron argument we draw. And so these three parameters, which I'll talk more about as we go along, are the gravitational wave frequency, the frequency derivative, and the advance of the periastron frequency. So these all come from the catalogue as well. So once we have these parameters, we can create a simulated system and put it in LISA data. So so we're using software called Balrog, which is being developed in Birmingham and also elsewhere, with which the objective is to be able to do LISA data analysis, to generate data and do parameter estimation with LISA sources. So there's several papers using this software, and we're actually in the middle of trying to make the code public. So we're really hoping that we'll be able to have it in a easy to install format and you know, available for people to use quite soon. At the moment, we're mainly working on documentation, but these things take time. And okay, so we use Balrog to generate the data, and having done that, we want to see if we could recover what we injected. So we do Bayesian parameter estimation for each of the 300 systems using the same software. This is the same table as before, so the same 11 parameters, but all we've added on are the prior range if people are interested to know more. And at the end of this, we get the result of our analysis is a posterior distribution on each of the parameters. So this shows one example of a system that we've run, a black hole binary system. And so this density plot shows the recovered posterior. So you've got the amplitude and the inclination here, the periastron precession frequency and the frequency derivative, the sky position, so ecliptic longitude and latitude, the total mass. So these are the sampled parameters. So they are contained inside this table. And then from those sampled parameters, we can derive the parameters about the physical parameters about the system, so the masses. And this is what we're interested in working out, whether we can measure those masses well enough to be able to tell they are black holes and neutron stars. So these are 4 key parameters that we'll use in our investigation. So I should have said the little star is where the injected binary is. Okay, so we've got our parameter estimation results for 300 systems, and we think about there's 4 key parameters that will help us to work out whether we can distinguish these systems. So one is the frequency of the gravitational wave. And for our systems, this is always well measured. So these are like near monochromatic systems. So they're sort of clear against the measuring the frequency. It's relatively easy. The next parameter we're interested in is the frequency derivative of the gravitational wave. So this is shown here. So the frequency enters into this there, and also the Chert mass, which is what's important for us. So the Chert mass is this combination of the 2 mass parameters, M1 and M2, where as I said, M1 is always bigger than M2. And the eccentricity enters into it as well. So with this equation here. So if we can measure the frequency derivative, we can try and get some constraint on the chirp mass. And then similarly, we can use the frequency, the periastron precession frequency, which depends on the total mass, so M1 plus M2, and the gravitational wave frequency, and also the eccentricity. So now we've got a couple of equations where we can measure these quantities and then convert them into the masses, the chirp mass and the total mass. But we also want the eccentricity because we need to be able to measure this to place a constraint too. So here we show both of these equations, and the idea being that if you can measure these 4 parameters, you can convert those into masses, M1 and M2. Okay, so so this is what I've just said. If we can measure these 4, we can measure the chirp mass and total mass, and then the component masses, M1, M2. And you need to decide what are you going to say is a measurable system. So this is the choice that we make. You could have made a different choice, but for our purposes, this is what we did. So we take the median of the parameter. So this is the parameter that you're interested in. So you could put the frequency derivatives in here, and then 3 times the sigma of the posterior on this parameter. And then we call this our measurability statistic. And if it's greater than 1, we say that it was measured. So
about the periastron precession frequency, why it's not 0 when eccentricity is 0? Because why it's still if your system doesn't have eccentricity, shouldn't this, or is it only applicable when the system has eccentricity?
Oh, that's a good question.
We can discuss later.
Yeah, I might need to think about that one. I guess maybe someone in the room might actually know better than I, but yeah, I'll think about that one. Thanks. Yeah. And okay. Yeah, so we've got these parameters that we'll try and measure, this criteria. So this is an overview of the parameter estimation results that we've got out after we've done the conversion from the sample parameters to the mass parameters. So here we've got the chirp mass and the total mass, and then the 2 component masses, M1 and M2. And then the colors are, so the binary black holes are up here, the black hole neutron stars here, and then the neutron star binaries here. And this is, the crosses indicate the extent of the 90% of the posterior distribution. Okay. And then perhaps I should have had these the other way around, but what we do is we apply this measurability criteria, and then we see how many of each of these parameters and the parameter combinations we can call measured. So these are the individual ones. So for the frequency derivative, we measure 29 of the binary black hole systems, 47 of the black hole neutron star systems, and then 60 of the binary neutron stars. So what we're really interested in is cases where we can measure all 3. So it's 13 of the black hole systems, 10 of the black hole neutron star systems, and then 49 of the neutron star systems. And what you see here is the count of the measured systems. So maybe if I go back here, this is showing the ones that were measured. So you see that we do indeed have a lot more of the neutron star binary systems than we do of the others, and that we do less well with the black hole binaries. And then this is showing the cumulative distribution of the systems that we measure. So you see there's parameter combinations up here. The gray areas are because there were no binaries in the draw at that point, and they are ordered by frequency and by SNR. So you can see that in the example of the neutron star binaries, you don't measure many at low frequency, then suddenly it jumps up at the sort of mid frequency and then tails off at the higher end. And then I guess similarly up here, but shown in black is the systems where we can measure all three. So these are shown down here. And yeah, I think you're right. Yeah, I think you're right there.
Also could be number of cycles.
You see this in the
Yeah, you get to, yeah. Yeah, I think that's right. And I think the number of cycles might play into it as well, because the frequency is at a different, typically lower. Yes. Okay. So so then we want to ask ourselves, will we be able to distinguish them? So it's one thing actually measuring the parameters, and then maybe another thing to be able to separate them from the white dwarf binary systems. So what we see is that the black holes are pretty easy to distinguish based on the masses. So this plot is showing the component masses for the black hole neutron star system. So this is M1, so these are all the black holes, and this is M2, so these are all the neutron stars. And what you see here is that the black holes are typically above, say, like the 3 solar mass kind of level. So we could pretty confidently say these are black holes, especially in cases where we measure them very well, like these guys here. But then if you look at the neutron stars, the extent of the posterior distribution is quite a lot broader. So you maybe would not be able to distinguish those with absolute confidence from a white dwarf binary system. I don't know how I'm doing for time. Oh, okay. I think I may have rattled through this a little bit too quickly, actually, because we're almost reaching the end. So apologies for that. But I have some extra slides at the end that we could discuss as well, if you're interested. Okay, so having picked up these systems, what we then are quite interested in is really how many concrete numbers should you expect from the least emission. So it's one thing saying that you can measure approximately 10% of binary black holes, 10% of black hole neutron stars, and then 50% of the binary neutron star systems, but then it's 50% of what? So for this, we go back to the catalogue that we have drawn our binaries from. So in that population study, they also predict how many systems you might expect from least emission of 4 or 10 years. And they, well, inside there, they use quite a lot of different models for the systems that they, for the galaxies they simulate. So different models of like, for example, the common envelope phase of the binaries and all of these different kinds of tweaks that you can do with these population studies. So what they end up with is quite broad ranges of predictions. So shown here is these are their predictions, and in brackets is the 10-year mission, and then without brackets is the 4-year mission. So 6 to 154 is quite a broad number, but it's I think it's not 0 is a wonderful estimate, really. So these are the number of detections. And then the number of, then for our purposes, we'll try and see what number you could get with measurable masses. So this is not just detecting the system, it's measuring the masses. So we simply do, so it was about 10% of the black hole binaries, and we get these numbers here. 10%-ish of the black hole neutron star binaries, and then about 50% of the neutron star binaries. So I guess what we can conclude from this is that we should expect to see maybe a handful of systems that we can also measure the masses for, which will be really nice, and to be able to detect these. So I've reached the summary, but so just to overview, Lisa's going to bring lots of new science in the mid-frequency range, so 0.1 millihertz to 1 hertz. We're long-lasting systems from signals from binary black holes and neutron stars will be amongst this population of white dwarf binaries, and we should be able to measure masses for at least a few of these, and have a handful of detections during the mission. So I have reached the end, so I'm sorry I went a little bit under time, but we have, if you have any questions, then I'd love to chat. And I have a few extra slides if we wanted to discuss more. So maybe, yeah, I could stop there and if you have questions. Yeah.
I would ask about so I have several questions. So thank you so much.
Oh, good.
But so to start, like just the first curiosity is that have you looked into the correlations between certain mass parameters or eccentricity and so on, and how well you can measure the mass? Because the only way you are breaking the degeneracy to compute actually the component mass is through eccentricity, if I have understood correctly.
Yeah.
And so higher the eccentricity, you would hope that you will distinguish M1, M2 better for the fixed SNR event, for example. Have you seen that, or
that's a good point. So I think, so you mean that you would be able to, for high eccentricity, you should be able to.
Same system, I fixed the SNR. One is with lower eccentricity, one is with higher eccentricity. And just to know that if eccentricity really just is the only parameter which gives me this, because you show the population stuff, which is astrophysical and great, but for data analysis people like us, I want to also see that is one parameter, just because normally I should not be able to measure mass ratio if it is circular, right? So or just show mass, and that's it. So have you looked into, sorry, so this is linked into the eccentricity correlation with the mass measurement?
No, we haven't yet, actually. So I think yes, I'll write this down because I think it would be a great thing, because it's all it's a work in progress at the moment. So I think that's definitely something we should take a look at.
And the other one was the advance of periastron. I don't know, I didn't see the equation, but I would also assume that your monochromatic assumption for eccentric early in spiral should break for
so they're near monochromatic, so they do drift, but they're not, it's not a monochromatic signal, so it's like chirping slowly.
I see. So it's but like for eccentric systems, I would expect like you will have a, if I go to extreme eccentricity 0.9 or so, in that case you have this blip of signal and then no signal, and this is just a broadband signal.
But don't you expect to get them like I guess the various harmonics of the signal? So you have a strong signal.
Yeah, there will still be a dominant. I see.
Yeah.
There will be still some dominant harmonic, which would be again, okay, maybe you're so early in the spiral that it doesn't. But
I think how is you have a dominant harmonic, but then also contributions from the higher harmonics as well.
Yeah, but not the higher multiples, just higher eccentric ones.
Okay.
Just because the signal is maybe.
Yes, good point. I maybe need to think about it for the long time as well.
No, because we are very eccentric here.
Okay.
So we are just sticking on to, something that we know we are holding on to that.
But I think the question is, what is the natal eccentricity distribution?
What's the eccentricity distribution? Okay, so most of them were quite low, but there were some in the catalogue that were very high, like a level that we probably were unable to truly model the signal. So I think there was maybe some at 0.6 or 8. So and then for our analysis, we're only modeling the first 12 harmonics. So you're definitely missing some information.
Oh, you are. I see.
Yeah.
I see. So you have and because you have in frequency domain, so you have some different harmonics in the frequency.
Yes, that's right. Yeah.
For
Oh,
the
sorry, I
eccentric-
should have.
The same, yeah, I see, I see.
Yeah.
Ah, I see.
They're using Klein's model, EFP.
That's the also important.
Sorry, yeah,
The
no,
normal-
we'll discuss maybe during later.
Yeah.
More details.
Yes, yeah.
Thank you for the talk. Just for curiosity, so Balrog, how long did it take to run these 300 round estimation rounds? And I guess you did it for each single source separately, right?
Yeah, so it was like 300 jobs. Some of them took a few hours and some of them took a couple of hours. So it just, I think it depended on the system and how the sample is going, but it was that kind of range.
So I have a question more on the catalogs that were used to create a population, right? And also related to eccentricity. So are these catalogs considering only the common envelope evolutionary channel or also the evolutionary channels in the dynamical ones, basically?
So I think it's both in there. I'd have to double check to make sure, but I know they have in their paper, they did a lot of different variations of the ingredients, I guess, for the population synthesis.
So because I guess in the cluster case, you typically get more eccentric populations of everything.
Yeah.
So it goes back to this, so you mentioned you had some cases where the eccentricity is very high.
Yeah.
So I was wondering whether these are the ones that can.
I don't know what you're saying. Yeah.
Because my understanding is that this catalog, in general, the population models are still, as you showed, actually, the numbers are very uncertain. Right? They are more uncertain than the uncertainty of the measurements, basically, of all the parameters.
Yes, that's true. Yeah, but I'll check back about that, but I'm not 100% sure.
Other questions?
I can ask you. So I think one thing is this catalog, if they are considered, because if the eccentricity is non-zero, it's mostly coming from maybe dynamical channel. But I was wondering why the mass distribution of black holes is only up to 10 solar mass.
Yeah.
Oh, okay, why?
Because if they're in dynamical channel, they could be higher also, right?
Ah, good point.
Yes.
Oh, yeah, good
And
point.
also the distribution you showed, can you please,
Yep.
in which you were showing this across the plus errors on, this one.
All these ones, yep.
It's seems like most of the system are close to mass ratio 1.
Yes, and this has been quite challenging in the sampling, actually. So this is, I mean, this is what is in the catalogue, but then for us being on that limit, we're sort of at the edge of the sampling region, and then we have the prior boundary that we've, the boundary of what's physical. So it has made quite challenging for the sampling. And then I can show you in here. So this is what, these are the neutron star systems, and this is why we end up with the star is the injection, and then the band is the extent of that's the extent of the posterior distribution with the 90% in the box. So this is what we've been finding, that it's quite challenging to be able to sample these, and while we're skewed at the edge because they're all on this almost on the mass ratio 1. Yeah.
So I think the question is also that like typically we expect the more massive the system is, the more should be SNR. But in this case, neutron star binary has more SNR. Does that mean they're more closer to merger than the black holes? Is this a fair statement? Or
Why is that?
Yeah. I'm not certain, actually. Yeah.
And I'm assuming none of them are going to merge in LIGO because they're in our galaxy. Otherwise, LIGO would have seen something. Probably.
Oh no, these are way before merger, so it's much earlier.
But also because LISA launch in 2025 is not a special year, right? Is that so that means if they exist, they should merge sometime. So if LIGO has not seen anything, then maybe these binaries will never like either SNR will be too low or they will be
right. But isn't it also just a what's the word? A selection thing, that because LIGO is observing many galaxies, then you are more likely to see one than you would in our own galaxy. Just
No, that's true, but I was just thinking in grand scheme of things,
Mm.
20 years is nothing compared to 5 million years, so.
Yeah, okay, yeah, that's true.
But okay.
Yeah.
We can discuss later.
Yeah, yeah, okay. Oh, true.
Yes.
Yeah.
Hey.
So I also had a question about background.
Mm.
And so what is the main difference? This is a variation different package, no? What is the main difference with other package like BB and why you need to use background for this analysis?
Well, I guess we've been putting, it has, I mean, against Bilby, it has systems that are unique to LISA. So I don't think Bilby looks for lifelong duration things.
Background brings his own waveform generator or can call other waveform generators?
I can call other ones. So I know like Geraint Pratton has been putting in IMR film waveforms into it. So it uses that technology. And then it does use other people's samplers as well. So it uses things like Dynasty and Nesse. And then, but it wraps it into a thing where we've modeled LISA sources.
But then the particularity, what it is that it brings the LISA response.
Yeah.
It interfaces with the LISA
Yeah,
response.
yeah. So it has the TDI response in it.
And has his own TDI, or also it can also use the TDIs of other people.
Yeah, I think we could. It has its own at the moment, but I think as things come together, I think maybe, well, like with the DDPC, I guess we've tried to make it quite modular so that if we want to switch out another piece from somewhere else, then we can do that. But
currently, do you know if the LISA response is computed in the time domain or in the Fourier domain?
I'd have to check back about that. Yeah, I think I'm still learning there.
I mean, in principle, well, yes, if they are using, I guess they are using the Fire PE, of getting for the phasing eccentric. So that should be in Fourier domain. But
I think I need to talk to Antoine.
I just one day.
PTA question.
Please,
Okay, so, thanks. So, we also have maybe a couple of new consider boundaries.
Yes.
Plus, so I was wondering how that could affect the detection rate that you showed in the last slide. Like, can you consider how except future studies how that could affect the detection of these systems, given the fact that there is still without sources. I guess this will go into the global problem, right?
Yeah, exactly. So yeah, at the moment we're only putting in the sources through. I mean, so a massive doctoral binding.
It's a different frequency.
Yeah, to pull them out because we're looking at narrowing frequency boundaries for the system. I think it would not affect
At least to be
The same,
right, because you have many.
either those that are resolvable, but also those that are formal
Yeah, so I wonder if you might misidentify an enzyme as one of these.
I have a PTA curiosity.
Okay.
So what do we have to do to actually then finally, with a lot of evidence, say that, okay, we have detected, like, what do you need more? Like, do you need more data? Do you need more analysis time?
Yeah.
Do people need to agree that everybody should be making a unified statement for PTA with IPT? Well, I just want to know what is the outlook for PTA discovery? Like, one can go around saying that, okay, it's a discovery without any controversy. So what is really missing there?
I think, to me, I think it's probably a combination of things. So at the moment, what was released by the individual pulsar timing rate groups was a evidence, which was between 2 and 4 sigma, I guess, depending on which pulsar timing array team you talk to. So the longer you observe, the better your sensitivity gets, is one thing. And the more pulsars you have, the better your sensitivity is as well. So this is the purpose of trying to have the IPTA, the International Pulsar Timing Array, data set. So that's where the different groups, because a lot of it's geographical. So the Parkes Pulsar Timing Array will mostly, of course, observe pulsars in the south, and European can observe in the north. And then when you add all the data set together, you can have a much larger array of pulsars. So that helps, but it's also very difficult because each facility has its own instruments, which are very different, different local settings, and the local, like the real experts within each pulsar timing array need to try and get the data set in a format where you can actually have an array with everyone's data. So that's very difficult. And that's why these data sets take a long time to come out. It's like the individual pulsar timing arrays are able to release their data and do the analysis on a shorter timescale than the whole can come together. And then additionally, what you want to be able to do is understand the noise in each pulsar, which isn't from gravitational waves. So gravitational waves is like a noise in your pulsar signal, but then you also have things that are taking place within each pulsar. So like they have the jitter noise, where the pulse profile changes a little bit each time. And most of them have some sort of red noise inside just intrinsic to the pulsar. So there's a lot of challenges going to trying to model those as well. And yeah, so I guess the answer is maybe to continue combining the data sets, observing for longer, and like try and build up the
Do you
signal.
think combining the data set probably would result in a quicker increase in so where should one
Potentially.
prioritize? Either taking more data with some particular,
Oh, okay. Well,
or what do we,
yeah, I think
like that was my original
yeah,
question.
it's not easy to. Well, if you take the Meerkat pulsar timing array data set, for example, they've observed for 4.5 years, and they had I forget exactly the confidence in the detection, but it was comparable to the other data sets which have been observed for decades, and they've managed to do that in just 4.5 years. So yeah, it depends. I think there's a lot of things you can tweak, and then
Too many factors.
yeah. But I mean, I think Meerkat will keep going in terms of producing a very, very amazing data set. But the amplitude was much bigger. It was like twice as big as the other PTAs. So it's very interesting. Why is that? I don't know. But and then I guess the SKA will transform it as well. So that's a long answer to.
No, I understand.
So I guess we can think again.
Well, thank you.
Yeah, like that. So it's hard to